Hello everyone, welcome to my lecture series of electromagnetic fields. We will discuss different theories, phenomena and numerical solution of different cases in this series. I hope this series will give a fruitful outcome to physics scholars or engineering students. In a previous video, we have derived an expression of electric field intensity due to infinite line charge. Press the I button to view that content. Today in this video, we are going to derive an expression for electric field intensity due to finite line charge and due to charged circular ring. So let us start. Now consider a straight line which carries uniform charge with charge density ρL coulomb per meter on it, having length of 2a units. Assume that the line lies on z-axis from minus a to plus a and its midpoint lies on origin. So we are considering a three-dimensional Cartesian coordinate system and we are putting a line charge of length 2a unit with ρL charge density as its midpoint lies on origin. Now assume a point P on y-axis at which intensity is to be determined, and let the distance of point P from the origin be small d on y-axis. So here our point of interest is P, on which we are going to derive the electric field intensity. And assume a small length dl which carries a charge dq along the line, and let the distance of dl from origin be z on the z-axis. We know that if we want to determine a electric field intensity on any point due to line charge, then first we need to determine the intensity due to differential length on the line charge, and then we need to take the line integral of that particular intensity throughout the length of line. So first we are going to determine the intensity due to this dl. So considering this dl, we first need to have a distance vector from dl to point P. So in this case I have mentioned it as r bar, and the direction of the intensity due to dl will be the same in the direction of distance vector. So now the small charge on the differential length can be written as ρL, that is charge density, into length of that differential element. So here the length is dl, but as it is on the z-axis, we can write ρL into dz. And the distance vector, that is very important term for the calculation, can be written as rp bar, that is position vector of point B, minus rdl bar, which is position vector of differential length. So rp bar can be written as 0x bar plus day bar plus 0 az bar. So as you can see, the point P is on y-axis, that is why its x and z coordinates will be 0, and y coordinate will be the distance of point P from the origin. With the same logic, we can also write dl bar is equals to 0ax bar plus 0ay bar plus z az bar. So as you can see, the differential length lies on the z-axis, hence its x and y components will be 0, and the z component will be the distance of dl from origin, which is z in our case. Putting the values of rp and rdl bar in the equation of distance vector, we will get distance vector equals to day bar minus z az bar. And modulus of distance vector can be determined by taking the square of its x, y and z coordinate, then adding the squares and taking the under root. So modulus of distance vector will be under root d square plus z square. The unit vector, by its definition, can be written as the vector itself divided by the magnitude of the vector. Now the intensity due to differential length dl can be determined with the help of the equation de bar equals to k dq divided by modulus of r bar square into ar bar. So just by putting all the values in the last equation, we will have d bar equals to rho L dz divided by 4 pi epsilon 0 into square of under root d square plus z square multiplied by the unit vector in the direction of distance vector. Now for every charge on positive z axis, there is an equal charge on negative z axis as well. So we have a small charge dq on the length dl, which is separated with z units from the origin. We can also have another charge dq in the negative z direction. Fine. So due to this second charge, let us say that differential length is dl prime. So due to that dl prime, one intensity will also can be determined on point P, and the direction of that intensity will be dE bar prime. Fine. And if we understand both the intensity by segregating it in their components, then we will have two components in y direction and two components in z direction. And we can see that the components of z direction will be in equal magnitude and opposite direction. So this dz prime and dz will cancel out the effect of each other. So we can conclude that a z component in this equation will have no importance in the calculation. So we will eliminate this term az bar from the calculation, as we know that the field intensity will have no z component in this case. So the z components of field intensity at point P will cancel each other, and only y component of E bar will exist. Moving further, now we will just consider the y component of field intensity. And now integrating above equation over z axis from negative a to positive a, that is the throughout length of line charge, we can obtain the total electric field intensity on point P. So total field intensity can be written as line integration from negative a to positive a d rho L dz divided by 4 pi epsilon 0 d square plus z square raised to 3 by 2. Here the d square plus z square raised to 3 by 2 can be seen as, here we simply take multiplications of numerator and denominator. Fine. So in numerator it will be d into rho L dz. Now ay bar, it is just showing the direction of field. Fine. So I have kept it aside. In denominator 4 pi epsilon 0 multiplied by this term, which is nothing but d square plus z square to the power 1, because here it is under root and whole square. So under root and square will cancel out each other. So simply it will be d square plus z square power 1. And this term under root d square plus z square can be written as d square plus z square power 1/2. And having the same operands, the multiplication, the power will be added. So d square plus z square to the power 1 plus 1 by 2, which is nothing but 3 by 2. So this term in the denominator comes in this way. So finally we are having a equation, and now we need to perform the line integration. But here, as you can see, the integration should be performed with respect to z, and we are having that variable in the denominator with power 3 by 2. So it will be very difficult for us to calculate such integration, and at this point we will take help of variable manipulation. So from our previous video, we are aware that variable manipulation can be very effective to reduce the computations. So let θ1 be the angle from point P to one end of line charge with respect to horizontal axis. So here I have considered the upper end of the line charge is making an angle of θ1 with point P with respect to horizontal axis, which is y-axis in this case. So as you can see, the θ1 is in an angle between upper end of line charge and point P. And similarly, let theta 2 be the angle from point P to other end of line charge. So the down end or another end of line charge is making an angle theta 2 with point P, and here point P is making an angle theta with our differential length. Fine. So we are going to use these angles as a variable manipulators. So now we can say that z equals to d tan theta. So if you consider this triangle, say this right angle triangle, then for this triangle tan theta is defined as the ratio of opposite side, that is z, to neighboring side, which is d. So we can write z equals to d tan theta, and from this equation z equals to d tan theta, we can also write dz equals to, so it is just we are taking the differentiation on both the sides. So dz can be written as d will come out as a constant, and differentiation of tan theta will be sec square theta d theta. And now let us manipulate the limit of integration. So for z equals to plus a, theta 1, see, for z equals to plus a, now consider this triangle. So in this triangle where z equals to plus a, then tan theta 1 can be defined as a divided by d, and hence theta 1 will be tan inverse a by d. Similarly, for z equals to minus a, now we will consider the lower triangle, say this one, and for this triangle tan theta 2 is defined as negative a divided by d. So theta 2 will simply be tan inverse minus a by d. So putting all these values, z equals to d tan theta, dz equals to d sec square theta d theta, and the limit from minus a to plus a, we will take theta 2 to theta 1. We will have an equation that E bar equals to integration from theta 2 to theta 1 rho L d, then in place of dz we have put d sec square theta d theta whole divided by 4 pi epsilon 0 into bracket d square plus, in place of z square we will write d square tan square theta raised to 3 by 2. Moving further, we will have all the constants out from the integration. So we can have rho L upon 4 pi epsilon 0 integration from theta 2 to theta 1 d square sec square theta d theta whole divided by d cube 1 plus tan square theta. Now this 1 plus tan square theta is nothing but sec square theta, that is very popular trigonometric identity. So simplifying further, we will have 1 upon d sec theta d theta, and keeping d as a constant, and 1 upon sec theta equals to cos theta, then the integration part will be considerably simplified after taking variable manipulation. So this is the benefit of variable manipulation in integration process. So now E bar can be considered as a integration of cos theta, which is nothing but sin theta. Lower limit is theta 2 and upper limit is theta 1. Putting the values, we can have an equation of field intensity at point P as rho L upon 4 pi epsilon 0 d sin theta 1 minus sin theta 2 AR bar. Fine. Here AR bar is the general form of equation. Fine. It shows that you need to consider the distance vector. Actually this should be capital R. So we need to consider the direction of distance vector. Okay. So from this equation we can find the electric field intensity due to any finite line charge on any point in the space. Here theta 1 can be determined by tan inverse a by d, and theta 2 can be found out by tan inverse minus a by d. Fine. For unsymmetrical distributions, we just need to determine the angles between both the ends and the point of interest P. Fine. Now the second topic, which is electric field intensity due to charged circular ring. So consider a charged circular ring of radius r placed on xy plane with its center on origin, and it carries uniform charge along the circumference with line charge density rho L coulomb per meter on it. And assume a point P on z-axis at which the intensity is to be determined. Let the distance of P from the origin be small z on z-axis. Also assume a small length dl which carries a charge dq along the line, and here cylindrical coordinate system will be more suitable for the calculation, as the ring can be imagined as a part of cylinder, and every point on the ring can be easily represented with the help of cylindrical coordinates. So for this derivation, we are not going to use Cartesian coordinate system, rather we will use cylindrical coordinate system. So it depends on the case which coordinate system should be used for the derivation. Fine. So as per the discussion, this Cartesian axis is just for our reference. Fine. In actual calculation, we will use cylindrical coordinate system. So we are assuming a ring on xy plane. Fine. And the radius of this ring is r, and line charge density is rho L coulomb per meter. Now there is a point P on the z-axis at the distance small z from the origin. So we have a point of interest named as P. Now if we want to assume a differential length dl, then we can assume it on the x-axis. Fine. So that the angle can be eliminated from the calculation. Fine. Because we know that if we want to calculate any vector in the cylindrical coordinate system, then its second coordinate will be the angle phi. Fine. But if we take the differential length on x-axis, then that phi will be 0. That is why for the simplicity I have taken dl on x-axis. Otherwise you can take it anywhere on the ring. So here is a distance vector from dl to point P, and this is the direction of Ez bar. Now we have divided the intensity in two components. One component is along z-axis and second component is along the direction of r. So as you can see, this is the component of intensity along the direction of r, and this vertical component is a component of intensity along the direction zx. So here dq, or the small charge on differential length, can be written as rho L into dl. Here differential length in cylindrical coordinate system can be written as, say, this angle, that is the starting and ending point of differential element, this angle is d phi. So in place of rho L, we need to keep this length, which is nothing but r into d phi. Fine. So the simple formula for trigonometry, arc equals to radius into angle. So here radius is small r and angle is d phi. So dl is nothing but r into d phi. The distance vector can be determined by rp minus rdl bar, which is position vector of point P minus position vector of differential length. And the position vector of point P in cylindrical coordinate system can be written as 0 AR bar. See, because point P is on Z axis, so its R and phi components will be 0. Only the Z components will be non-zero, which is equal to the distance of point P from the origin, so which is Z in our case. Similarly, the position vector of DL can be written as R AR bar plus 0 A phi bar plus 0 AZ bar. So as this DL lies on x-axis, find the only component in the direction of radius will be non-zero, other two components will be 0. And doing so, we can have the distance vector as minus R AR bar plus Z AZ bar. And the magnitude of distance vector will be under root R square plus Z square. The unit vector in the direction of distance vector can be found out by taking the division of the vector with its magnitude. And finally, using this simple equation and putting all the values in this equation, we can find the intensity due to DL on point P. Once we determine the intensity, then we will take the closed line integration from 0 to 2 pi. Fine. So this is the fundamental essence how to derive the expression. So finally, we are having an equation of electric field intensity due to DL on point P as shown in the screen. But for every charge on the front half of the ring, there is an equal charge on back half of the ring. So if we divide the whole ring in two parts, then let us say this part is front half and this part is back half. So if we are having a small charge dq in the front half of the ring, then we can also have a small charge dq in the back half of the ring. And due to this part, that is dl prime, an intensity on point P can be determined by dE prime. And if we take two components of dE prime as we have taken in case of dE, then also we can have two components, one in the direction of Z and second one in the direction of R. And as you can see, these two elements, that is DER prime bar and DER prime, are equal in magnitude but opposite in direction. Fine. So both these components will cancel out the effect of each other. So the net effect parallel to the plane consisting the ring will be 0. That is, the component of R direction can be eliminated from the calculation. So from this point, this is the component of R direction which can be eliminated from further calculation. So this will save our time. So in this step, I have eliminated the component of R direction and taken the multiplication of numerator and denominators. Fine. So finally, the equation that we get is rho L R Z d phi divided by 4 pi epsilon 0 into bracket under root R square plus Z square raised to 3 by 2 AZ bar. Here AZ bar shows the direction of field intensity. So as you can see over here, the direction of field only exists in Z direction. Now integrating above equation with respect to phi from 0 to 2 pi, we can obtain the total electric field intensity on point P. So now we are going to integrate. See here, the limit of integration will be 0 to 2 pi, so that the closed line integration will be there. So doing so, the total field intensity can be written as integration from 0 to 2 pi rho L R Z d phi divided by 4 pi epsilon 0 into bracket under root r square plus z square raised to 3 by 2 az bar. Now this is very simple form of integration, because as you can see there is no term consisting phi in the whole equation. Fine, so all the things will come out as a constant, and finally integration of 1 with respect to phi will be calculated, which is nothing but phi itself. So E bar equals to rho L R Z phi lower limit 0 upper limit 2 pi whole divided by 4 pi epsilon 0 into bracket under root r square plus z square raised to 3 by 2 az bar. And simplifying further, we will have the final equation of electric field intensity at any point P due to charged circular ring as rho L R Z divided by 2 epsilon 0 into bracket under root r square plus z square raised to 3 by 2 az bar. So for any case in which we need to find the electric field intensity, the selection of coordinate system is very essential in order to reduce the calculation time and calculation efforts.